Now we need to see the kinetics of corrosion. So, let us start with kinetics of corrosion. When we start talking about kinetics of corrosion, first of all we need to know how to express the corrosion rate. Whenever we talk about kinetics, that means we involve the rate of corrosion. So, we need to know how to express corrosion or dissolution rate. So, this corrosion or dissolution rate can again be further bifurcated into two modes. One is weight loss per unit area per unit time. The another mode is the current density. Now, the weight loss per unit area and per unit time is simply you have to measure the weight of the metal in the solution for a particular duration and then see the loss in weight divided by the area of the surface area which is exposed to the solution and the time duration. That would give me the weight loss per unit area per unit time. Now, again the current density also can lead to the same thing, weight loss per unit area per unit time, and these two units, those two modes can be related through some conversion factors. Now, first let us come to this weight loss per unit area per unit time. This mode is simply, let us say you have weight loss of about 1 milligram and the area exposed is 1 decimeter and the time duration is 1 day, then I can measure this unit as 1 milligram per decimeter per day, which is expressed in the form of MDD, which is a very popular unit to express the corrosion rate or the dissolution rate. Now, this looks peculiar, but this is the convention. We took it as milligram per day per decimeter per day. Now, the point is here one important factor is why we need to divide this weight loss with the area. Now, let us say you have two beaker and now you have kept the same solution, HCl solution. Let us say you consider HCl solution of same concentration, of same purity. Now, you put a iron piece of same composition, let us say it is a pure iron, it is 99.999% pure iron, and here also you are keeping the same metal iron with 99.999% pure iron, but the area which is exposed to the solution is different in both the cases. Let us say in this case the area is more. So, both the cubes of iron, same composition, same solution, same concentration, but you have a different area which is exposed in the cases. Now, in this case the area exposed is less. So, if you consider A1 and A2, so A2 is greater than A1. Now, if you try to measure the corrosion rate in terms of weight loss per unit time, or let us say milligram lost per day in this case, and in this case also you measured in the form of milligram per day. Let us say one day you have kept it, the pieces are kept for one day in the same solution. Now, since we are using the same metal, same solution, we are not changing anything else. Only thing that is changed is the exposed area, but since the material is same, metal is same, so we should get the same corrosion rate. But you will see that the corrosion rate in this case is more than the corrosion rate in this case. It should not happen like that. Why it is happening? Because you have more amount of exposed area, which exposed area in the HCl media of the same concentration. Now, how to make it same? If then this should be more, because since we have more exposed area, and the one important factor with the corrosion is corrosion always happens on the surface. So, if it is happening on the surface, so more surface of the same material would lead to more dissolution. Okay. So, in this case the dissolution is more, that means weight loss is more, but since the corrosion rate should be same for both the cases, because you are not changing anything except you are changing the area. So, how to make it same? So, the main thing is we have to normalize this corrosion rate with respect to area. How to normalize it? You just have to divide it by another parameter, which is area and then day. So, you have also, you just have to divide it by area and per unit day. So, then this inequality will not be there, then this will be equal. So, corrosion rates are becoming equal since the material is same. That means you have to have this area factor associated with the corrosion rate expression. And now, once you know this, then it is very clear that why we are introducing the area. Now, the SI unit for rate expression is SI unit is basically nothing but gram per meter square per day. So, you can express in the form of MDD or gram per meter square per day, and the experiment how to do this, how to get to this unit. For that you need to do a little bit of experiments. The simple experiment is expose this iron piece in HCl for a day or some few more days, and then take the sample out, measure the weight, final weight, initial weight minus final weight is the weight loss, and then you know what is the area exposed to the solution. So, that divided by area divided by the number of days, that would give me the MDD. Now, this is very clear, because whenever we have iron in HCl medium, HCl acid, then you are going to get dissolution. But now we see that there are two modes. One is weight loss per unit area per unit time, the another one is current density. Let us see where from this current is coming. Now, whenever have, let us say, a small section, let me consider a small section, I just blow it up, let me blow this section, the cross section wise, let us say this cross section I am blowing it. So, now this is my cross section. This section is exposed to the solution medium, and this side is also exposed. Now, if you consider this side, now we can have somewhere, you can have the dissolution of iron, and when you dissolve iron in the form of iron, so you release 2 electrons 2 electrons are released, and these 2 electrons will go through the metal piece to a section where you have cathodic reaction. Now that means electron is flowing from anodic section, current flows in the opposite direction. So the current flow would be in this way. So if current electron flow is this way, current flow would be the reverse way, and then you have a circuit. In the solution, the current will also flow from the anodic side to the cathodic side. You can have the same analogy in case of galvanic cell, where you have the copper cathode, you have zinc anode, and through the external circuit you have electron flow from the zinc side to the cathode side, and in the solution you have current flow from copper side to the anodic side, which is zinc. So now you can have a current flow. Now the amount of ion that is dissolving, that would be having a direct relation with this current that is flowing in this circuit. Now that relation is given in the form of, there are two laws which tells you the relation between the two laws which give you the relation between the metal dissolution and current that is flowing in the circuit. Now these two laws, the first law says, now let me get into the two laws. The first law says it's the amount of chemical change. The chemical change here, it is metal dissolution, which is also can be considered as electrochemical change, where metal is dissolving. So the amount of metal dissolution or iron dissolution in this particular case would be strictly proportional to the amount of current or the amount of electricity that is passed through the electrolyte. Now that means it says that the amount of chemical change here, in case of corrosion, let me put it as dissolution. I am saying that amount of chemical change or the dissolution or the corrosion, dissolution is nothing but corrosion, would be proportional to the amount of electricity. Amount of electricity. Let us say if the loss is metal loss or the metal dissolution is W, then W would be proportional to Q amount of charge. And now we know that Q is nothing but IT is proportional to I into T. I is nothing but the current, and T is the time for which the current is passed through the current is passing in the circuit. So now this is one, and then W is basically nothing but ZQ, and Z is electrochemical equivalent for a material. How to know Z? Let us say in case of silver, so this reaction is possible since silver is highly electropositive metal. So it is a noble metal, so reduction process is taking place, and we know what is the atomic weight of silver, 107.88 gram per mole. Now here we know that the number of electron that is involved for this reduction process is 1. So 1. Now if we would like to find out what is my electrochemical equivalent, that means how much metal silver will be deposited on the silver electrode per coulomb. So, now from this we can measure what is the gram equivalent. In this case, since one electron is involved, so gram equivalent would be for silver would be equal to Ag by N, which is nothing but the number of electrons that are involved for the reduction process. Here N is 1, so let me put 1, so which is nothing but the molecular weight. And we know that if we supply 1 Faraday of electricity, then the change would be equivalent to 1 gram equivalent, 1 gram equivalent weight. So, if you supply in this case 1 Faraday electricity, then this much gram of silver will be deposited, since here gram equivalent is equal to the molecular weight. Gram equivalent is equal to atomic weight. Now, in case of iron, here 2 electrons are involved, and iron we know what is the atomic weight. Atomic weight is 55.85, and that case equivalent gram equivalent would be 55.85 divided by 2, since there 2 electrons are involved for the reduction process, or other way around, if iron is coming out as iron, so it is oxidation process. Now, that means 1 Faraday is equivalent to Ag, since gram equivalent is equal to Ag. So, 1 coulomb would be equivalent to Ag by 96500 coulomb would be equal to, you can measure this, then 0.000118 gram. So, here Z is equal to, which is nothing but Z of silver. Now, we have some relation between the weight loss or the dissolved weight is equal to the gram equivalent into the total charge. Now, second law, first law would be enough to have a relation between the weight loss per unit area per unit day with the current. But let me also put forward the second law. Second law says that, let us say, if you are supplying the same amount of electricity, then the amount that would be deposited or dissolved would be chemically equivalent. That means, in case of voltaic cell, let us say you have this zinc, in case of this is zinc sulphate solution, and this is zinc plate. Now, you have connected to a copper plate in copper sulphate solution, and you have completed the circuit with a salt bridge. This is copper sulphate solution, and if you maintain the activities of zinc and copper constant, and if you connect these two terminals, you will say that current will flow from this end to this end. This is current flow, and this end to this end there will be electron flow, and copper will be deposited here, zinc will be dissolving in zinc sulphate. Now, when you have this, then if you supply the same current for the same amount of time, same duration of time, then you will see that amount that would be deposited on the copper side and amount that would be coming out from the zinc electrode to the zinc sulphate solution will be chemically equivalent. That means that E, let us say E is my chemical equivalent, okay, would be proportional to Z, which is my electrochemical equivalent. So, this is the second law, but the first law would be enough to have a relation between the current and the corrosion rate. Let us get into that part. Now, I know what is I. I is nothing but dq dt. So, rate of charge flow or the electron flow is basically the current. Now, if you know this, now we also know that if, let us say, for this reaction Mn plus, let us take a general reaction Mn plus Ne equal to M, in case of metal M. Now, this is a reduction process. Now, we are concerned with the corrosion. So, instead of reduction, let us write in the other format where the metal will be dissolving in the form of Mn plus ion, and then Ne number of electrons will be released. So, let me put this reaction in other format. M would be equivalent to Mn plus this. So, in this case, let us say I supply 1 Faraday of electricity, then this would be equivalent to gram equivalent. So, in this case the gram equivalent would be, if A m is my atomic weight of metal M and there are n number of electrons that are involved for this oxidation process, then it would be n. This would be my 1 Faraday would be this much gram of metal M will be coming into the solution. So, if this is the situation, then if we supply q amount of charge, then what would be the total, what would be the number of moles that would be released into the solution? If q is the charge, then q by Nf would give me the number of moles. Then this would be my, let me put n dash to be the number of moles that would be released in the form of metal n plus m plus ion, Mn plus ion. So, now if we know this, and this n dash is nothing but, let me put this, n dash is the number of moles, and Am is nothing but the atomic weight of metal M. So, if we can get this relation from this. Now, this relation I can take it as dq by dt, Nf I am taking out, since N and F both are constant for this particular reaction, F is always constant. So, now this would be equal to dN dashed by dN dash dt, the rate at which the metal is dissolving, or the rate at which the number of moles of metal M is dissolving in the solution would be equal to this. Now, from this we are now relating to the amount of metal that is dissolving, that means this N dashed. Now, dq dt would be Nf dN dashed dt. Now, let me replace dq dt with this. So, let me put, now let me consider this. So, here I would be equal to 1 by Nf dN dashed dt. Now, so what is my dN dashed dt? It would be equal to I divided by Nf. So, dN dash dt, which is the rate at which the number of moles is dissolving in the solution in case of metal, would be equal to the current divided by number of electrons that are that is involved for this oxidation process, and F is 1 Faraday. Now, N dash is nothing but, I can have a small relation for N dash. N dash is nothing but the weight, let us say W is my weight loss. If W is my weight loss, then what would be the number of moles? Would be equal to AM. AM is basically nothing but the atomic weight of metal M. So, I can replace N dash in the form of A W divided by A cap atomic weight of metal M. So, it would be equal to, now I just replace this N dash, now I can put W AM. Now, I can take this AM part, which is atomic weight of metal M, to that side. So, I put it as AM. Now, this is another relation which tells you the weight loss per unit time equal to current into the atomic weight of metal M divided by NF. Now, we have already come across from this that it is not good to express corrosion rate in the form of weight loss per unit time, because the corrosion process is happening on the surface. So, it is better to divide it by the area to have a better representation of corrosion rate, and which can be comparable. For comparable, we have seen that process in case of the same metal piece, two pieces of metal, two pieces of iron dissolved in HCl of same concentration, and the only change is the area in one case is smaller, the other case is bigger. So, that case, in order to have the comparable corrosion rate, it is always better to divide it by area. So, now same way we can put it as, we can divide by area of the metal piece which is exposed to the solution. I put A, which is the area that is exposed to the solution. Now, similar way I can also divide this part with A, and here A is nothing but the area. So, now I have this relation, let me write it here. So, dW A dt would be equal to dW dt divided by area would be equal to current into AM, which is the atomic weight of the metal M, divided by NFA. And this is done just to have the unit weight loss per area per unit time. Now, this part, if you see, if you consider, if you want to see the value of AM, N and F, all are constant for a particular process. So, that case I can take this AM part, NF part on the left side separately. I can consider these two parts, AM, these three values, and then I can have I by area. Now, for a particular metal M, these are constant. So, only variable is this. Now, if these are constant, and now you see that the rate of corrosion is exactly proportional to I by A, and I by A is written in the form of I, small I, which is considered as current density. Which is considered as current density. Now, if this is a constant, so now from this relation it is pretty clear that the corrosion rate is proportional to current density. So, now I can write that I can, let us say, if we remove all those dw dt term, and if we integrate it with respect to time, so then we can get W divided by area into time would be equal to AM by NF I, or I can write corrosion rate proportional to current density, because this part is constant. This part is constant. So, now if you see these two modes, these are basically the same thing. In one case you find out the weight loss, and in many cases you will come across that the weight loss is so marginal, it is better to find out what is my current density. So, once you know the current density, you can express this current density in the form of weight loss per unit area per unit time. Fine. So, this is one important relation. Which combines these two different modes of expression for corrosion rate, weight loss and current density. Now, in case of this is fine, let me put forward another situation. Let us say in case of crevice corrosion or pitting corrosion, these two modes, the another mode is uniform corrosion. This and these two, you will, Professor Chaudhary from IIT Roorkee will cover this part, but for the time being let me tell you, this uniform corrosion means the corrosion is happening. Let us say if this is my exposed surface, the corrosion happening uniformly throughout these sections, throughout the areas. Now, in case of pitting or crevice, you will experience, if you have the same thing here, okay. Now, the corrosion would be happening if you consider the same piece of the same cross sectional area and area exposed to solution, you will come across that corrosion is happening in some localized regions. Localized regions, these regions corrosion is taking place, and the corrosion is penetrating inside the volume, inside the metal. So, if we would like to understand the rate expression, corrosion rate expression for this and this, let us say in this case I determine the corrosion rate in the form of MTD. So, that will be fine, because the corrosion is happening throughout the section and overall exposed area, everywhere corrosion is happening. But in this case, few sections or the few localized regions we are experiencing corrosion. So, this mode will not be proper in this case. So, in this case we need to measure the corrosion rate in the form of depth penetrated divided by time, since overall cross sections are not coming into picture. Fine. So, that case, how would we convert this same expression, this relation into the form of depth penetrated per unit time? Now, let me write. So, you can understand that in case of uniform corrosion, the rate expression what we are using, for example, MDD or metal loss per unit area per unit time, will not be good for expressing the corrosion rate in case of crevice or pitting, where the corrosion is happening in the localized region and corrosion is basically the pit what is forming, that is penetrating inside the metal, and overall our surface area remain intact. So, that case we need to understand how to express the corrosion rate. So, that case we express the corrosion in the form of depth of penetration depth of penetration by time. Now, you will see that this expression can lead to the expression for the pitting or crevice. Now, let me write W divided by A, which is area, into time would be equal to current density into AM divided by NF. Now, if I divide this with the density of the metal, let us see what happens to the left side. To the left side, what happens? Now, I divide by a row. So, I have to divide this right hand side also with the rho, which is the density. Rho is density of metal. Now, that case, what would be the unit that is coming out, dimension for this left side? Now, weight is mass, then area is length square, time is second, and this is mass divided by length q, which is the density. So, this is coming out to be length by time, length by time, and this is in taken. So, let me put it as time. So, length by time. So, now if I just divide this part with the density of the metal, I can easily convert this MDD unit to a depth of penetration per unit time unit, and so this would be then would be equal to W A into T into rho would be equal to I into AM NF rho, which is another important relation to express the corrosion rate for crevice or pitting or extremely localized corrosion or dissolution. So, now this is another expression. So, in this case I know what is the unit, length by time, and the convention, US convention, in order to understand the depth of penetration per unit time or the express the rate in the form of depth of penetration per unit time is nothing but milli inch per year, and this also called as mils per year, and in short form it calls at it is called as MPY. Now, in SI unit, this is US convention. Now, SI unit, it is written as millimeter per year. So, now we have two units, MPY and millimeter per year. So, now we know that we can express the rate of corrosion in the form of metal loss per unit area per unit time. We can also do it in the form of current density. We can also use the unit MDD, which is milligram per decimeter per day. We can use the unit for depth of penetration. One is MPY, one is millimeter per year, and that is used for crevice or pitting or extremely localized corrosion, and MDD is used in the case of uniform corrosion. Now, with this concept, let us chalk out some problems, solve some problems, then things will be much more clear. Now, let me write these two expression on the right side corner. One is W A T equal to I A M by NF. This is for uniform corrosion. This is one. Second thing is WAT rho is equal to I m by NF rho, which is for crevice or pitting corrosion. So, let me remove other part and let us find out, let us solve some problems. Now, first thing, let us find out what, let us say one convention is, another convention is you can find out what would be the corrosion in the form of MPY if you know the weight loss, if you know the area exposed, if you know the time duration, and of course, if you know the density of the metal. So, one convention is if you know the weight loss W in the form of milligram and T in the form of hour, density in the form of gram centimeters cube, and A, which is area, in the form of inch square. This is, there is no such meaning why we are using milligram, hour, gram per centimeter cube and inch square. This is a convention we take. Now, if you have this mode, then we know what is my weight loss, okay, we know what is my NF, what is my T, what is my area, what is my T, and what is my rho. If you see the relation, this is my relation, which is again length by time, and I have mentioned that this can be expressed in the form of MPY, and the relation is says that this should be, if these are the expression mode, milligram, hour, gram per centimeter cube and inch square, then this into 534 would be equal to MPY. This would be the number of this would be the MPY, which is the corrosion rate in the form of milli-inch per year. Now, how would we get 534? The 534 is nothing but the conversion factor. Now, since this is in milli-inch per year, I need to convert everything in the form of milli-inch, in the form of, so that we come across this unit. Let us see, if we know this, if we know this WAT rho, if I put all those units, let us see what happens. This is 1 milligram, this is 1 inch square into this is hour, 1 hour into this is 1 gram centimeter cube. Now, this should be, I just convert into gram, so that gram can get cancelled. So, this would be equal to 10 to the power minus 3 gram divided by 1 inch square. Let me put it in the form of millimeter milli-inch. So, if we take it in the form of milli-inch, so it would be 10 to the power 3 10 to the power 3 square just a minute, let me first put it in the form of inch square, then hour, let me convert into year, because here we have year. So, 1 hour would be 1 by 24 into 365 1 year is equal to 365 days and 24 is the number of hours in a day. So, 1 hour would be equivalent to this year, and 1 gram, and inch, let me convert it into centimeter, centimeter cube in the form of inch square, inch cube. So, 1 centimeter is equal to 1 by 2.54 inch. So, it would be equal to 1 by 2.54 cube into inch square. So, this inch cube. So, this things are getting cancelled. Now, this should become, so now this inch will go in the numerator. So, 10 to the power minus 3. Now, let me convert this inch into milli-inch into 10 to the power 3. This should become milli-inch, and then this term will also go to the numerator. So, milli-inch into, let me put it, this term, let me put it on top. So, 10 to the power minus 3 gram is getting cancelled here, into 10 to the power 3 milli-inch into this part will go above. So, 24 into 365 . This would be, this is per year, and this should be divided by 2.54 cube. So, if you do this calculation, you will see that this value is coming out to be 534. Yes, 534. So, this is nothing but milli-inch per year, which is nothing but MPY. So, then you see that this conversion is coming because of the unit conversion. So, now this is one way to express the corrosion rate. Now, let me also, this is the problem number 1, why we get this 534 conversion factor in order to convert this W by AT rho in the form of MPY. And the second problem, let me chalk out here. Let us see, the problem says that iron is corroding at a current density of 1.69 into 10 to the power minus 4 ampere per centimeter square. So, what would be the corrosion rate in the form of MDD and in the form of MPY? So, these two things we have to find out. Now, we know these two relations. These two relations will give me the corrosion rate in the form of MDD and MPY, because we know the relation between current density and weight loss per unit time, per unit day, weight loss per unit time, per unit area. Now, let me chalk out the same problem here. Let me remove this. For understanding MDD or express MDD, the corrosion rate in the form of MDD, so we have to use the first expression. because here we know that this part gives me the weight loss per unit area per unit time. So, I will use first term, and here I know only thing I know, that is the current density, and other things what we know. In case of iron, we know that iron is dissolving in this way, and I know what is my Fe 55.85 gram per mole. So, this is equal to I, AM and F. So, here I is 1.69 into 10 to the minus 4. So, 1.69 into 10 to the power minus 4, and I know this light side we consider right hand side into, I know what is AM, A 55.85, I know what is N is 2, F is 96500. Now, I need to find out what is, this is basically, let me put it in the form of units, this is ampere per centimeter square into 55.85 gram, this is coulomb. Now, this I can write it in the form of 1.69 into 10 to the power minus 4 coulomb per second per centimeter square into 55.85 gram divided by into 10 to the power 3 milligram, since MDD is nothing but milligram per unit per day per unit time per unit per decimeter. So, this would be equal to 2 into 96500 coulomb. If you, this will get cancelled. Now, second you convert it into day, centimeter square you convert it into decimeter square, then you will get, if you convert all those things, you will get that this value would come 422.54 MDD. So, only thing what you have to do, second you have to convert it into day, centimeter square you have to convert it into decimeter square, because 1 centimeter is equal to 10 centimeter is equal to 1 decimeter. This conversion if you do here, then you will get that the corrosion rate is coming in the form of MDD, and this would be equal to 422.54 MDD. Thank you.